Hello guys, in this video tutorial I would like to explain the estimate of the parameter, the unknown parameter of a distribution by using the method of moments. Uh, method of moments is one of the method which can be used to estimate the unknown parameter of a probability distribution. And this video will have a general procedure, and then in the next video, in the next or the coming videos, I will discuss about some specific distribution like binomial, Poisson, negative binomial, etc. The method of moment estimation general procedure. Let f of x theta be the PD probability density function of a random variable x with parameter theta, and that's is a vector. Suppose theta 1, theta 2 up to theta p, a vector of unknown parameters. Suppose that the first r moment about 0 exists, about 0 or about origin exists. So remember that there are two types. I will just discuss two types of moments here briefly. That there are two types of moments. One is about origin or 0, that is called raw moment. So we will use raw moments for the estimation of the parameter, in this case in the method of moments. And the other moment is or the moments about mean. So we will not use that, we will use raw moments, and we denote these moments by mu r prime, like this mu r prime, which is the expected value of x power r. So this means that if suppose I'm calculating the first moment of the first raw moment, that will be mu 1 prime equal to e expected value of x power 1 or expected value of x only. If I'm interested in the second moment, second raw moment, and remember that this is population, these are population moments. So if I'm interested in the second population raw moment, then that will be equal to mu 2 prime equal to expected value of x square. So the statement says that suppose that this statement says that suppose the first r moment about 0 exists, or you can say the expected value of a particular moment, suppose rth moment is less than infinity. This is the same statement that if this moment exists for r equal to 1 to up to p. Suppose these events exist, this population, the first r population raw moment. In general, this mu prime or this should be prime, this is these are raw moments. Mu r will be the function of the parameters theta 1, theta 2 up to theta p, and you will see these the moments that these are the function of parameter in the next videos, in which we will solve some distributions, some example. Okay, so this is about the raw moments of population. Now if x1, x2 and x up to xn is a random sample from a distribution f of x theta, then the earth sample moment, which means that the earth sample raw moments is defined as m r prime equal to 1 divided by n I from 1 to n x I power r. I explain two moments for this because normally we need two moments. If the distribution have two parameters, then we need two moments. I will explain this later when we will need to solve. So this means that this is general earth sample raw moment is m r prime equal to 1 divided by n I from 1 to n x I power r. So okay, let me explain this for the first two moments. Suppose this is m1 prime, this is equal to, because I just put r equal to 1, so this means that this become 1 divided by n I from 1 to n x I power 1. So we don't need to write power 1. So this is just the formula of the sample mean, 1 over n I from 1 to n x I, that is equal to x bar. The second moment m2 prime, which is equal to 1 divided by n, just replace r with the 2 in the general formula. M2 prime equal to 1 divided by n I from 1 to n x I square. I will explain this at the end of this lecture, that this is also equal to m2 is equal to some other value which is simple. So I simplified this. At the end of the lecture you will see. Okay, so we discuss about this raw population moment and the raw sample moment, and now it can be easily verified that expected value of the earth sample raw moment is equal to the earth population raw moments. This means that this sample earth raw moment is an unbiased estimate of the population raw earth moment. This should be estimate. Okay, so this means that mr prime is an unbiased estimator of the mu r prime. Now what we need to do, so this is just about the sample or raw moment and population raw moment. Now we need to have some mechanism to solve and to estimate the parameter of unknown parameter of some particular distribution. In the moment method, the estimates are denoted by theta 1 with this notation, theta 2 and theta t with this notation. So these are the estimate of the parameters from 1 to p, and we know this by these notations for the parameter theta 1, theta 2 up to theta p. They are the roots of the system of equation given by. So what we need to do actually in the moment of method, we just need to compare the raw moments. I mean that this is mu r prime, this is the earth population raw moment, which is equal to m r prime, which is the earth sample raw moments for r equal to 1 to up to p. Whatever is the number of parameter in the distribution, we need that number of moments. So if a distribution has one parameter, we will need to calculate only one sample raw moment and one population raw moment, and then we will compare and solve for the parameter, whatever is the parameter, so we will get that parameter. If we have two parameter in our distribution, then we need to calculate two population raw moments and two sample raw moments, and then we need to compare first population raw moment with the first sample raw moment, and second population raw moment with the second sample raw moment, and then we need to solve those equations to calculate, to estimate the unknown parameter. Okay, in the other word, the solution of mu r, this should be raw moment, so prime, and this should be prime. So in other words, the solution of mu r prime is equal to m r prime for r equal to 1 to 3 up to p yield these estimated values. This means that when we solve these equations, I mean that we will have p equation if we have p parameter, and when we solve those equations, we will get these parameters. So in other words, the solution of mu r prime is equal to m r prime for r equal to 1 to p yield theta 1 with this notation, theta 2 up to theta p. So these are the estimate, the moment method estimates of the parameter. Okay, now I just explain. We know that in the first sample earth moment, that is equal to x bar. You can see that I explained that here. That is here. Mu1 prime is equal to 1 divided by m1 prime is equal to 1 divided by ni prime 1 to nxi. So this is equal to x bar. And I explained the second moment at the end of this lecture. So that is, you can see here. Remember that m2 prime is equal to summation xi divided by n, summation xi square divided by n. This is by definition. And now we know that s square sample variance is equal to summation xi square divided by n minus summation xi divided by n whole square. So just replace this with the x bar, because this is summation xi divided by n, that is equal to x bar. So this will become x bar square. So s square is equal to summation xi square divided by n minus x bar square. Now just shift x bar square on this side, so this will become summation xi square divided by n is equal to s square plus x bar square. And now this implies that m2 prime, which is equal to summation xi square divided by n, and which is further equal to x bar square plus s square. So you need to know that m1 prime is equal to x bar and m2 prime is equal to x bar square plus s square. Okay, now you have this sample moment. You need to calculate the population moment. This means that you need to calculate m1 prime, that is e of x, and mu2 prime, which is equal to e of x square. And then you need to compare these moments like I did here generally, like this. And then we need to solve these equations for the unknown parameter. And if you have more parameter, you need to calculate more moments as well, and you need to make more equations for the solution. So thank you very much for watching.